Hi everyone, welcome to this Unit 4 review, Part 1. This is going to go over, I believe, moments, as well as like other free body diagram type problems. So these are AICE past paper problems, and don't forget to subscribe. A child on a sledge slides down a hill with acceleration a. The hill makes an angle theta with the horizontal. The total mass of the child and the sledge is m. The acceleration of free fall is g. What is the friction force of F? Okay, so if the child is sliding down the hill with acceleration a, and the mass of the child on the sled is m, that means that the total resultant force is equal to m times a. Or this is just the going down force. So we also have to account for gravity too. So this is going to be gravity, so then this is theta. I kind of drew this wonky. So this is kind of just like perpendicular to the slope, and this is the gravity part. So the gravity constant will be going down the hill. It's going to be sine theta times our mg here, because since this is mass times gravity based on the child's weight. And then since this is gravity, our gravity plus our friction force is going to be equal to our resultant force, which is ma. So then if we do a simple algebra here, we do ma times sine theta, or oops, ma minus sine theta times mg is equal to f. So m times a minus sine theta g is equal to f. And it turns out that since f is going in the other direction, this is just going to be negative, kind of. So our answer is C. Okay, so a box of mass 8.0 kilograms rests on a horizontal rough surface. A string attached to the box passes over a smooth pulley and supports a 2.0 kilogram mass at its other end. When the box is released, a frictional force of 6.0 newtons acts on it. What is the acceleration of the box? Okay. So let's try and label the forces that act on the boxes. So for example, here on the box, when we let it go, we have a box that we have the frictional force of going 6.0 newtons to the left. Another thing we have to consider is that once the box is released, both of these boxes go accelerate at the same amount of speed. So our resultant force for B, the total resultant force is going to be like 8.0 times A, where A is the answer because that's what they're looking for. And there's also a tension force here that pulls the box on opposite ends. So for the first one, the box, we have 8.0 A is equal to t minus 6.0 newtons. T is going to be in newtons. Yeah. For the small box, it's going to be 2.0 A is equal to well, this is T, and then we have a gravity constant that goes down 2.0. So it's going to be 9.81 2.0 minus T, because T is going in the opposite direction. So we have a two variable equation here. Let's go ahead and add these together. So we get 10 0A is equal to the T's cancel out, so it's 9.81 times 2 minus 6. If we got a calculator out, it will be around 1.4 meters per second squared, which is A. What is the definition of the force on a body? So let's look at each of these. We have to make sure that it actually matches our description of force on a body. So we have the mass of the body multiplied by its acceleration. Sure, that's the definition of a force, but not necessarily like on a body, I'm pretty sure. But I think this is viable because if you think about it, what I said was wrong, sorry, but like if we have a body here, the force on this is going to be mass times acceleration, right? For the second one, the power input to the body divided by its velocity. This is not necessarily it, because we're talking about force, not about like electricity, I'm pretty sure. Yeah. For C, the rate of change of momentum of the body. So this is the rate of change of this, or rate of change of T. This may be it. And then for D, the work done by the body divided by its placement. So work over D. So I think for this answer it's going to be C, because it's talking about momentum, right? Momentum is when the body moves despite inertia. So in this case, it's going to be C. Okay. A uniform meter rule is pivoted at 34 centimeter mark as shown. The rule balances 164 gram mass is hung from the 4 centimeter mark. What is the mass of the meter rule? Okay, so this is about calculating moments. And our pivot is here, I'm pretty sure. Well, we can assume that it's like our pivot is on this line. And recall that moment is equal to force times distance from pivot. So in this case, it's going this way. Our weight is going from the left and down, so then it's going to be anti-clockwise. So we need the distance. So this is at 4 centimeters, right? And then if we go to the pivot, it's 34 minus 4. This equals to 30 centimeters. So So it's gonna be sorry. I should say that it's not 0.3, but it's 30 centimeters times 64 grams times 9.81 meters per second, because we need it in force. Technically, all of this should be in Newton meters. But since everything is kind of like in the same units, so like this is in Newton, this is in centimeters, and this is in centimeters, we can kind of neglect specific units, because they're all scaled by the same factor anyway. We just have to make sure like they're in the same general units. So then this is anti-clockwise, and now we need to count the clockwise. The clockwise is, in this case, starts from gravity, for example, right? But it goes from the middle of the ruler and goes down. So when you calculate the distance from that, it's going to be 15 minus 34 is equal to 16 centimeters. 16 centimeters times the mass in grams times the gravity constant, yeah. And since the rule is balanced, we can just set these two equations equal to each other and calculate for m. So 30 times 64 times 9.81 is equal to 16.0 times m times 9.81. Just cancel out, and you're left with this becomes 4. 120 is equal to m. So our answer is then C. A ladder is positioned on an icy frictionless ground and is leant against a rough wall. At the instant of release, it begins to slide, which diagram correctly shows the directions of the forces P, W, and R acting on the ladder as it slides. Okay, so we have our diagrams here. We can see that the only things that really differ are the position of the R's, for example, right? So some of them go inside, some of them are just straight up, and some of them go out. Since the ground is frictionless, then we know that there is no force going left and right. It's just simply the normal force. So in this case, R should be going straight up. If you think about it, imagine you have a ladder, but it's like on the ground, on dirt, and you're against the wall, right? The weight of the ladder keeps it going from falling out from the bottom here. That's because there's some force going inwards here. So if it was a normal ground, it would point inwards, but since there's no friction, there's nothing holding the bottom of the ladder like inwards. So it's like not C or not D. But we see that it's actually leant against a rough wall. So that means there is some force opposing the ladder from going down. So in that case, it should be going up. So in this case, it's just the only viable answer is going to be B. A rod PQ is attached to P at a vertical wall as shown in figure 3.1. The length of the rod is 1.6 meters. The weight W of the rod acts 0.64 meters from P. The rod is kept horizontal and equilibrium as a wire attached to Q and to the wall R. The wire provides a force F on the rod, 44 newtons at 30 degrees to the horizontal. Determine the vertical component of F. Okay. So we need to find the vertical component of F, and to do that we need to find what is it? We need to find the magnitude of F. So in order to do that, we're given the weight W, I think. We may need to do moments, as well as cancel out vertical and horizontal components. The wire provides a force F on the rod, 44 newtons at 33. Okay, so my reading skills are not very high right now. So they actually give us the magnitude. It's 44 newtons. So in this case, we can just use a sign because we know that our force is going like this at a degree of 30 degrees. So then we can just use the sine trig function to get the component. So it's going to be sine 30 degrees times 44 newtons, which is equal to 22 newtons. Oops. The horizontal component of F is just going to be the opposite, but it's going to be the cosine function. Which is equal to 38 newtons. By taking moments around P, determine the weight of W of the rod. Okay. So we're taking around this pivot, and then find the weight W based on moments. So we need to find clockwise and anti-clockwise, and they need to be equal. So our anti-clockwise is going to be the weight, right? Or sorry, the clockwise is going to be the weight. And it's going to be the distance of the pivot, which is 0.64. Times the weight in newtons. And the anti-clockwise is going to be the length of this, which is 1.6 meters, times the vertical component, which is 22 newtons. So then we get the equation that 1.6 times 22 is equal to 0.64 meters times weight newtons. And you just have to calculate this out. Which is going to be 55 newtons. Explain why the wall must exert a force on a rod at P. Well, it has to exert a force because the resultant force is equal to 0. The horizontal component of the string so then as a result, horizontal comp of wall is also not equal to 0, and thus it must exert force. On figure 3.1, draw an arrow to represent the force acting on rod at P. Label your arrow with arrow S. Wait. Draw an arrow to represent the force acting on the rod at P. Okay. Turns out that it's just gonna be like this. It's just S. And it's gonna be the same magnitude as the horizontal component of F. In which example is it not possible for the underlying body to be in equilibrium? So an aeroplane climbs at a steady rate. So since it's at a steady rate, the force is equal to 0. The resultant force, I should say. And if an aeroplane climbs, right, it'll climb like this, with an angle of theta across the ground. So then the torque is also equal to 0. An aeroplane tows a glider at a constant altitude. So at a constant altitude, this just kind of assumes that it's moving at a constant speed as well. So then this can actually be in equilibrium. Where C, a speedboat changes direction at a constant speed. Alright, so this actually cannot be in equilibrium simply because that it cannot change direction at all. This just means that if we have a boat, right, there's some force that is going like this and changing the angle of the speedboat. So there is actually some torque going on the object. So thus our answer is going to be C. If you're confused by like my definition of equilibrium, this just means that the resultant force is equal to 0. The resultant torque is also equal to 0. Which of the pair of forces acts as only as a couple on the circular object? Okay, so a couple on a circular object is just going to be a pair of opposite, and equal forces. So we just have to look for that on these free body diagrams and see that A is actually a really strong conductor because F is going in opposite directions and they're seemingly in the same amount of magnitude. For B, these are not in the same magnitude, so it's not B. The same problem exists for C, and turns out that's not right. And for D, these are not actually in opposite directions because you can see that F here is going clockwise and this F is also going on clockwise. So they are going in the same direction, so it is not D. Thus our final answer is A. The diagrams represent systems of coplanar forces acting on a point. The lengths of the force vectors represent the magnitudes of the force. Which system of forces is in equilibrium? Okay. So let's try and eliminate some. So we can see that for A, this might be viable. Though the magnitude looks kind of questionable. If you add these two vectors, it'll be something like this. So it's possible. For B, this is not in equilibrium because they're going in opposite directions, right? Or they're going out in directions, but they're not in like equal magnitude, so it's not necessarily in equilibrium. For C, the same thing, kind of. Mainly because this magnitude is, I think it's too strong on the right. So then these two forces on the left, they're only about like to here. So when you add them, it'll have a resultant force of something like this. For D, this is also viable, kind of. But the main problem with this is that the vertical components are not necessarily equal. So you see this vertical component for this bottom vector is way larger than this component. So then it's not D either. So then we're left with A, which is our final answer. Yeah. I think there is some discussion about the right hand rule. I feel like that's kind of like the out of scope of this video. So yeah. Okay, which statement best describes a couple? Okay, so we know that a couple is something, it's like a pair of forces, opposite and equal, and they're often associated with moments, which is rotational stuff. So we're looking for mainly this. So at A, pair of forces of equal magnitude acting in opposite directions and produce rotational force. Okay, so we pretty much got our answer, which is kind of funny. This usually doesn't really happen, but let's look at the other choices just in case. So we see that in opposite directions and translational, but not rotational. So this isn't necessarily true because couples do act in a way such that it produces rotational motion. For C, they don't act in the same direction because that defeats the entire purpose of a couple. They go in opposite directions. And the same thing says for D, so then our final answer is A. A cross-shaped structure freely pivoted at O has arms of length 5.0 m, 4.0 m, 3.0 m, and 2.0 m. It is acted on forces 2.0 n, 3.0 n, 4.0 n, and an unknown force of F. The structure is in rotational equilibrium. So when the structure is in rotational equilibrium, that just means that some of the clockwise moments is equal to some of the anti-clockwise moments. So we just have to calculate these clockwise moments. And we have to go one by one because we can see that there are 4 different forces, but they go in like different directions. And we have to figure out whether or not they're clockwise moments and anti-clockwise moments. Okay, so for the clockwise moments, we have, or not the clockwise moment, for this first one, we have F and 5.0 meters. So we get that F newtons times 5.0 meters. This is assuming part of the clockwise moments. And then let's go to the next one. So we see that there's actually an angle here. This is going to be sine 30 times 2.0 n, which is actually equal to 1.0 n. So then our sum of anti-clockwise moments is equal to 1.0 n times 4.0 m plus 2.0 m times 3.0 n, which is equal to 10 and n. So since these two are equal, we get that Fn times 5.0 m is equal to 10 nm. So then F is equal to 2.0 n. which is B. The diagram shows a uniform beam PQ. The length of beam is 3.0 and its weight is 15 newtons. The beam is supported by pivot 1.0 with the load of weight hung from end P, and the beam is in equilibrium. What is the value of W? So the first thing you want to do is take the weight, because they give you the weight but they don't necessarily tell you where it is, where it's acting upon the beam. But it's going to be in the middle here, because based on the center of gravity, and since this is a uniform beam, it's just going to be in the very middle. And this is going to be 50 newtons as given. Since it's in the middle, it just means that from the side it's 1.5 meters, and from the pivot it's 0.5 meters. Since this is an equilibrium, the sum clockwise is equal to sum anti-clockwise. Our clockwise motion is going to be the weight of it, actually. So 0.5 meters plus, not plus, times 50 newtons, so equal to 25 newtons. The sum anti-clockwise is equal to weight in newtons times 1.0 meters, which is equal to weight newton meters. So then it turns out weight is equal to 25 newtons. Yeah. Forces are applied to a rigid body. The forces all act in the same plane, in which diagram is the body in equilibrium. So in equilibrium, that means that the sum of the force is equal to 0, and the sum of the torque is also equal to 0. So in A, we see that these two forces are going in opposite directions, so that means torque is equal to 0. And the vertical component, which is F, 1/2 plus 1/2 equals 1, and -1 here. So that means the sum of the force is equal to 0 as well. If we look here, we can see that this F goes down and this goes up. Since they're on opposite sides, they actually go in the same direction, which is clockwise. So then our rotational is actually 2F, and that means our torque is not equal to 0. For C, torque is equal to 0 because this F here are going in different directions, but they have the same magnitude. However, the vertical component of this is F plus F is equal to 2F, and there's an F going down, so it's minus F. So our resultant vertical component is F, which is not equal to 0. And you can apply the same reasoning to D. It turns out the resultant torque is not equal to 0. So it's not D, and thus our final answer is A.